Now, we will look at the effect of the small signal output conductance GDS of the MOS transistor on the common source amplifier. This is the common source amplifier structure we had. We have a source resistance of 100 kilo ohm in our previous example. I am taking exactly the same values that I had earlier, and we have these bias resistors which are made to be much more than RS, so that there is no voltage division between RS and these bias resistors. All of this Vs appears across the gate and source. And on the drain side, for biasing we need RD, and we have used a 100 kilo ohm load resistance, so that 20 volts is dropped across it from a 23 volt supply, and 3 volts are left across the MOS transistor, and the load resistance also is specified to be 100 kilo ohm. Okay. So, we know that the operating point in this case, this has already been worked out earlier. If you have forgotten the details, please go back to that lesson and work it out again. It will just be additional practice. Okay. So, the operating point is VGS of 3 volts, VDS of 3 volts, which corresponds to a drain current of 200 microamperes, and at this operating point, the small signal transconductance GM is 200 micro Siemens. This is what we had calculated. Okay. So, now the question is, what is the effect of the channel length modulation or the extra factor of 1 plus lambda VDS that appears in the drain current expression in the saturation region. Okay. Now, as was discussed earlier, the fact that we have channel length modulation means that the operating point current also changes, right, because here we get VGS of 3 volts, that does not change at all, because the gate current is still 0, but for a gate voltage of 3 volts, instead of the current being 200 microamperes, it will be dependent on VDS as well, and you can calculate it. But like I mentioned, usually we do operating point calculations without taking into account the effect of lambda VDS. Okay. So, we will assume that ID will remain at 200 microamperes, and therefore, VDS will remain at 3 volts and so on, and similarly GM will remain at 200 micro Siemens. Okay. So, we ignore the changes in operating point because of this. But we have the small signal picture of the same amplifier here, and if C1 and C2 are sufficiently large, now we do know how to calculate them to be sufficiently large. They do behave as shorts at the signal frequency. Okay. So, now if they behave as shorts, and if R2 and R1 are very large compared to RS, so let me write those things down. C1, C2 very large. I will not specify the value, but we do know how to calculate that, and similarly R1 and R2 are much more than RS. In this case, we know that the small signal gain V naught by Vs is minus GM RD parallel RL according to our previous calculation. Now, what is the effect of channel length modulation? Across the drain and source of the MOS transistor, we have a small signal conductance GDS. Okay. So, we have this additional conductance GDS. Okay. And again, we know that GDS is basically lambda ID, and if I take lambda to be 0.05 volts inverse, this GDS turns out to be 10 micro Siemens, or the reciprocal of 100 kilo ohms. So, the resistance that appears across drain source is 100 kilo ohms. Okay. Now, what is the effect of this? It is very easy to see. It simply appears in parallel with RD and RL. Okay. We have RD across the drain and source, RL across the drain and source in the small signal incremental picture. Now, this RDS or GDS also appears across drain and source. By the way, the notation GDS is used with the conductance and RDS is used with the resistance. So, RDS is 100 kilo ohm and it is basically the reciprocal of GDS. Okay. So, what happens, all these three resistors are in parallel, the current GM times VGS goes into the parallel combination of these resistors. So, the output voltage would be minus GM because of the polarity of the current times RDS parallel RD parallel RL, okay, times VGS, or the gain V naught by VGS would be minus GM RDS parallel RD parallel RL. Okay. Now, remember, this will only reduce the gain because we have an additional resistance in parallel with RD and RL. Okay. If you remember the sequence of events, we started off trying to make a gain of minus GM RL, and for the values of GM being 200 microsiemens and RL being 100 kilo ohms, we will have this value to be 20. And what we really get is minus GM RD parallel RL, because RD is inevitable and we can try to make RD higher and higher, but that will need a larger and larger supply voltage. If we choose RD to be 100 kilo ohms, the same as RL, then the gain will become half of what it was before. So, we get only minus 10. And finally, what we get is not even that, we have RDS also in parallel, and in this case coincidentally RDS is also 100 kilo ohms. So, minus GM RDS parallel RD parallel RL will turn out to be minus 6.7, 6.67. Okay. So, the effect of RDS is to reduce the gain of the common source amplifier, and in general any amplifier. Okay. One thing you notice is RDS appears in parallel with these. So, even if you set RL to infinity and RD to infinity, okay, somehow you find some way of biasing and there is no load resistance at all, the maximum value of gain magnitude would be GM RDS, okay, because this gain V naught by Vs, which is minus GM RD parallel RL parallel RDS, and if I consider only its magnitude, becomes plus, and we know that this is going to be less than GM RDS. Okay. So, this GM RDS both are just parameters of the transistor. Once you have a transistor and you decide its operating point, this number is fixed. Okay. And this tells you that there is a maximum limit to how much gain you can get from a single transistor. That gain number can be large or small, but there is a limit. Depending on the value of lambda and the operating point current you choose, you could have a larger or smaller number for this limit, but there is going to be a limit. Okay. So, even if you find magical ways of biasing where RD is tending to infinity and you do not have any load resistance at all, you still cannot get infinite gain from a single transistor. Okay. And this is anyway obvious if you look at the small signal picture of the MOS transistor, including the output conductance GDS or output resistance RDS. Now, this is GM VGS, gate, source and drain, and let us say that somehow we are able to establish the correct operating point in the MOS transistor without any extra component appearing anywhere. Okay. So, this is all the circuit we will have in the small signal. Let us not worry about how to do it, but if we do it like that, this is the circuit we have. So, the current here is GM VGS, all of it flows into the conductance GDS. So, this voltage will be minus GM by GDS times VGS, which is the same as minus GM RDS times VGS, and this is the gain that we are going to get at most. Okay. So, this GM RDS number is a significant number and it is the inherent gain limit of a transistor. It is not a fixed number, it also depends on the operating point. Okay. And like I mentioned in the lesson where we introduced channel length modulation, the coefficient lambda itself depends on the length of the transistor, but whatever it is, there is some upper limit to the gain that you can achieve. Okay. So, I hope this part is clear. So, for completeness, in MOS transistor small signal model, you have to include the output conductance. Now, because calculations are very cumbersome, we do not include it in the operating point and we do not include it for the calculation of GM and so on, although we could do it with some extra effort. So, unless otherwise mentioned, for operating point calculations and for GM calculations, omit the effect of lambda, but lambda will cause the MOS transistor to have an output conductance GDS, okay, and that you have to include into the small signal picture of the MOSFET in any circuit that you have, and of course, like GM, GDS also depends on the operating point, okay.